So let's start off with a little Boolean algebra before we get to K-maps. So let's look at an OR gate and the truth table for an OR gate, for example. And if we work out the Boolean algebra line by line, so wherever x is 1, to get x to be 1, you would have to have the negation of a and b, a and the negation of b, or a and b, because the top one, x, isn't 1. And so we can say in Boolean algebra that x is equal to the negation of a and b, or a and the negation of b, or a and b. And that's our Boolean algebra. But that's quite hard to sort of equate that to being an OR gate, isn't it? But what we're going to try and do is we're going to try and do this in a much more simpler way, and this is where Karnaugh maps come in handy. The example K-map that's shown here maps directly to the truth table here. So we say with negation of a, that's where a is 0, the negation of b where b is 0. What we fill in the boxes of the Karnaugh map is the value of x when you combine these two values. So the negation of a and the negation of b is the top row of the OR truth table. So they're both 0, and the output from x is 0. The negation of a and the second line and b being positive, combined together you get 1 as x. For a being 1, b being 0, the negation of b, the output for x is 1. And for a and b being 1, the output for x is 1. And that's how you build a Karnaugh map. But let's look at it in a bit more detail on the next slide. So let's look at these Karnaugh maps in a bit more detail and determine how we're going to actually use them. So from the previous slide, we've got the Karnaugh map for the OR gate here. And what we're going to do is we're going to try and work out what the Boolean algebra is just from this table here. So when we're looking at these things, we have to follow some rules. Number one, only ones matter. So these ones, these cells here, we can ignore that top left cell in the Karnaugh map. Second rule is that you should find even groups of 1 cells, so the ones I've ticked here. And they can either be in a row or a column or a rectangle, but then they can overlap, but it must be 2, 4 or 8 cells. So not entirely even then, you can't have 6. But you've got B there, that column, 1 and 1, and then you've got A and B at the bottom here, that row containing 2 cells. Rule number 3 is that any ungrouped 1 cells can be just called their own group. In our case, there is no ungrouped 1s, so we're fine, we can ignore this one. And with rule 4, this is probably the hardest bit of it, you only keep constant input values for each group. So I'm just going to highlight the first group in blue and the second group in green, and we'll talk it through. With the blue group, or the column, B is always the constant here. Okay, so B never changes, it's the column header, whereas A negates. And so from the blue group, we only keep B because it doesn't change. And from the green group, well, that's the row. A doesn't change because that's the row identifier, but B is negated, so B changes, so we don't keep that. And so all we're keeping from the green group is A. And then to create the final Boolean algebra, you just combine all the groups together. So it's A from the green group, or it's B from the blue group. And that is your output from a Karnaugh map. So let's look at this example. So we've got our Karnaugh map. We are going to identify groups of 2, 4 or 8 cells. And so we've got our 2 groups there. I'm going to just color code them. There's our green one for the row, and our blue one for the column. And I'm only going to keep the inputs which are consistent. So in the green one, the consistent input is A negated, and for the blue one, the consistent input is B negated. And so we have X equals negation of A or the negation of B. I don't know if that rings any bells to you, but if we apply De Morgan's, we can turn negation of A or the negation of B into A and B negated, which is a NAND gate. In a second example, you can see we've got 3 inputs, A, B and C, and so I've drawn the Karnaugh map for you. So let's identify the groups. So we've got a fantastic group of 4 here, so we can group them together. And oh look, we've got a 1 on its own here, which I suppose you could say is its own group, but actually this is another thing you have to know about. Groups, when you've got 2 or more input values, can be adjacent. So we've got an adjacent group to the right, but because it's 0 we can't use that, so we have to go left. But Karnaugh Maps loop, or sort of like wrap around a bit like a queue, so we can actually include BC negated with B negated and C negated into its own group. And if we were able to include this one, we could also include that, but we can't have groups of 3, we can only have groups of 2, so we stop there. So we end up with 2 groups. I'm just going to highlight them. I'm going to highlight the square in green, and I'm going to highlight the wrapped around pairing as well. So we've got 2 groups. I'm going to write them out. So in the blue group, the only consistent thing that doesn't change is A negated in the row. But look, we also have in the columns C is negated there and C is negated there. So that doesn't change because it's only B that changes. So we can have A and C individually negated. And if we look at the square, A changes because A is negated and A is not negated. C changes because C is negated and C is not negated, but B is constant because for that column it's B and for that column it's B. So our last part is simply B. And so our final Boolean algebra expression is X equals negated A and negated C or